course, we do not have to rotate exclusively around the x or the y axis. We can rotate around all sorts of different vertical and horizontal lines. So we want to let R be the region bounded by the curves y equals x squared, which is that curve right there, x equals 1, which is that vertical line, and y equals 0. So this region that I've shaded here. Assuming x and y are in centimeters. We're going to use the shell method to find the volume of the solid generated when that region R is revolved around the line, and we're going to do this twice. We're going to do this once with y equals 1. So, oh, that's a typo. Sorry. That's a typo. I mean x equals 1. I'll fix that. So that's because this is the one I have drawn here. So x equals 1 was what I was intending here. So we're going to rotate this way around the line x equals 1 right there. So that's our axis of revolution or axis of rotation. All right. So now remember, once that's your axis of rotation, once it's x equals 1, fix that typo, then you know that your rectangle must be parallel to that axis of rotation. Once you know that's fixed, then look down here at the bottom. You can tell that that thickness is dx, which means we are locked into a volume function. Let's think about it. It's 2 pi integral a to b r of x f of x minus g of x dx. We're locked in. We know it has to be dx. Once we know our axis of rotation is vertical, we know that the rectangle is parallel, therefore we know the thickness there is dx, and we're locked into a dx one. Okay, so let's think about this. For the dx, I'm going to need a couple of things. I need the radius, and I need the outer and the inner. All right, so let's look at the radius for a second. Yeah, let's do the radius. This is the hardest part for this problem. Okay, so now remember that this distance from here, let me do it, from here to here is x. I mean, that's what that represents, right? And then this distance from here to here is 1. It has to be. Now the radius of rotation, so remember the radius goes back to the axis of rotation. So it's the distance from the rectangle back to the axis. So the radius is right here. Oh, wrong color, sorry. R of x is equal to, all right, now how do I find that difference right there? That's 1 take away x, right? So it's 1 minus x. That's your radius. It's the distance of your rectangle from the axis of rotation. That's what your radius is. So there's r of x, which is actually a tricky thing to find in this problem. Now the height is actually quite easy for once. The height is very simple. It's the value of x squared, because it's from this x-axis all the way up, where we didn't cut it off down at the bottom. So it's just x squared. So it's x squared minus 0, because it's from this value on the curve down to this value down here, which is x equals 0. Right? So if you want to think of it in terms of, here, let me write this out. So this is 2 pi integral, I'll figure out my a and b in just a second, but I know that r of x is 1 minus x, there's r of x, times, and then f of x is x squared minus 0, because this line down here is 0. So it's 0 if you want to think of it that way. And then I know it's dx because that was locked in. Now the one thing I haven't found yet are my x values. However, it's pretty obvious, because when you look at this particular problem, you can see, hey, I'm going to start at x equals 0, and I'm going to end up at x equals 1 right here. Oops, I'm running out of space. So x equals 1, right? So that's my end right there, because my rectangle can zoom from left to right along this region. Let me show you in Desmos. There we go. So you can see x can go anywhere from 0 all the way up to 1, right? Okay, so we have that piece. So I'm going to go from 0 to 1. Lovely. All right, so then I have my volume formula, which is 2 pi integral of, and then I'm going to distribute x squared to both of these things. And of course, I'm taking the integral from 0 to 1. And then it would be 1 times x squared is x squared minus x cubed dx. Right? Okay, well, that's a very easy integral to do. That's 2 pi, that's 1/3 x cubed minus 1/4 x to the 4th. We'll take it from 0 to 1. And as with most polynomials, the 0 is irrelevant, so it's just 2 pi times 1/3 minus 1/4, which is 2 pi over 12, which is pi over 6. And I believe this was centimeters? Yeah, it was centimeters cubed. And of course, we can come up with a decimal approximation if we so desire. I actually have that in decimals already calculated. So if you click on the little arrow that shows you the folder with the integral calculations, you can see it's about 0.524. So, I have too many peaks in my M there. There we go. Now, obviously, the hardest part about that was finding that r minus x. That's actually the tricky part on this one. All right, but now let's revolve around a different line. Let's take that same region and we're going to revolve it around y equals 2. It's the same region. It's still between 0, x equals 0, or excuse me, y equals 0, x equals 1, and then y equals x squared. But this time, I'm going to rotate it around this axis of rotation. So then, again, it locks it in. I know that it must be that this parallel to that axis of rotation. It has to be. And that is a dy thickness. Just has to be. Okay, so then I have a dy thickness. I know that I'm going up to that. I need to think about my radius. My radius, well, I need to think about my length and my radius. Geez, both of them. There's going to be some work in this one. Okay, so the length is this distance right here. And now remember that our curve, which was given to us, is y equals x squared right here. But if y is equal to x squared, that means that x is equal to the square root of y. We're going to need that version of it in order to be able to do this problem, because we need it to be able to deal with it in terms of y. Everything is now based off the y-axis, not the x-axis. So when I want that length, what I want is this distance, which is 1, minus this distance, which is right here, which is the square root of y. So that means that that length must be 1 minus the square root of y. All right? Or there, I just recolored it to make it easier, and I kind of moved this down because I think I'm going to need some space up here, so I might as well make it happen. All right, so now I've got the length, right? Oh, and for the record, what I'm trying to do here is fill into my volume formula. I know that the volume has to be, because I'm locked into dy. It's 2 pi integral c to d r of y times, well, it's the length. So it's f of y minus g of y, but that is the length. And then I know I'm dy. This length right here, that's what we're doing. So f of y is 1, right? It's x equals 1. So x equals 1 is this line over here. So this is x equals 1 minus, and then the square root of y, which is y to the 1/2. So I have the length part now figured out. I have the dy part figured out. I have the 2 pi in front. I'm doing good so far. I need C and D. Okay, well, these are y values. So if you think about that region, the lowest y value is right here. So that's C. That's the start. And we end right up here. We end at y equals 1. I've kind of blurred it at this point, but that's where we end. So we end at y equals 1. So that's obvious. So I've got 0 and 1. The last part is the non-obvious part, which is the radius. Now, remember, the radius is the distance from the axis of rotation down to your rectangle. Now, remember, this rectangle is wide, but of course, we're talking about an infinitesimally thin rectangle. So you don't have to worry really about the width. All right, so what is that? Well, we're going to use that same logic we just did for the 1 minus the square root of y. It's 1, right, minus y. Because, here, let you see this. This distance right here is y. From here to here, right? From the x-axis up to that rectangle is y. The whole distance is 2, because that's 2 up there, right? So if I want r of y, what I want is 2 take away that little y piece. Because 2 take away this little y will get us the distance between the axis of rotation and that rectangle. So both of these are tricky. Both the length, 1, take away the square root of y, gets you 1 minus the square root of y, which is that length. This distance is 2, because that whole thing is 2. Take away that little y piece, gets you 2 minus y. So this right here is 2, take away y. Like that. Whew. Okay. So this was the radius, right? Right here. This is the radius of rotation. And that's the length, right? So this goes here and that goes there. All right, now that we're here, we can actually find this integral. We're actually going to have to distribute this. So this is equal to 2 pi, integral 0 to 1, 2 minus 2 square root of y, or 2y to the half. There we go, because I'm going to have to integrate this so it's easier to make it a power. Minus y plus y to the 1 times y to the half makes y to the 3 halves dy, which is 2 pi times 2y minus 2 times y to the 3 halves times 2/3. Oop, that's a 3. Minus 1/2 y squared plus 2/5 y to the 5 halves. Thank goodness we're taking this from 0 to 1 because the 0 is irrelevant. So it's 2 pi times, let's see, 2 minus 4/3 minus a half plus 2/5, which again, Desmos can help us with. This is what Desmos is good for. One of the many things Desmos is good for. So if I grab this example right here, so you can see it. There you go. According to me, it's 17/15, but again, I can type it. 2 minus 4/3, let's see, minus a half plus 2/5. Make it a fraction. Yep, 17 over 30. So it's 2 pi times 17 over 30, and then of course that reduces to 17 pi over 15. And then again, it's centimeters cubed, which is a decimal is about 3.561, or no, 3.560 centimeters cubed. I'm just writing those answers down before I take us back. There they are. Now, there's something very important to notice about this. Part A and Part B were the exact same region. I know it didn't seem like it, but they were. I just changed the scale. So 0 to 1, 0 to 1, 0 to 1, 0 to 1. Right here. 0, 1, 0, 1. So they're the same region, but the scale is different. But what did we learn about the volumes? So part A, rotating around the line x equals 1, got us pi over 6. Part B got us 17 pi over 15. They're very different, right? So that you can have the same region, right? We had the exact same region, may yield different volumes due to different axes of rotation. A different axis of rotation can make all the difference in what your volume is. It may happen. It's possible that it's the same as well, right? Both possibilities can happen, but a lot of the times they will be different depending on what the line is that you're rotating around.